We are live again. Hopefully, we will see many of you. We had a bit of a quiet live last night. I just did snacks with the kitty cats. They want their dinner, but I'm actually going to give it to them in a little bit of time. Maybe you'll even see that during this live. But yeah, I just wanted to catch up really quickly. If possible, tonight, I actually won't be able to go live later tonight in the dead of the night like we did last night, but maybe that's a good thing because last night I got a little bit sleepy. We talked about cosmology, we talked about some models of the universe, flat, open, closed. We talked about dark energy and how the model of the universe, depending on its evolution period, whether it's the very early universe, just after Big Bang, or whether it is sort of some 100,000 years, 300,000 years after the start of the universe, after the Big Bang, how it's basically how the content of the universe has changed and been dominated by different things. So we actually covered this last night from this book called Modern Cosmology by Scott Dodelson. We will see if we continue this topic tonight or if people want to do something else, but that's what we were doing last night. And it was a little bit sketchy in the sense that I was myself not super prepared with the material. I'm just kind of referencing the book here. But it's still fun to read about these things, and we can continue the discussion. It might be a little bit more smooth today because now I've done a little bit more study up on the topic myself. But pretty much we touched upon the concepts of, what the universe is, what cosmology is, how cosmology is different from astronomy and particle physics. And we talked about basically the Big Bang, nucleosynthesis, what types of light element abundances people expected and what they found, and also the cosmic microwave background and how that can be used to study the universe further. And things like that. And here is Baji. So welcome. Thank you for joining. If you're joining, thank you for being here. If you're seeing this as a video upload later on, thank you for watching. But yeah, that's what we did. And in the end of that, we also touched upon the fact that there might be some anisotropies in the smooth universe after all, which may lead to some theories about dark matter. So that's what we did. And we can recap some of this as well tonight. And if you're interested, we can get into it. Hi. Hello, Koi Bird. How are you? Koi says, hey, hello. We will actually share the live. Hi. Hello. Hi, Nadia. Hi, can I ask a question? Yes, Nadia, tell me. Derpel from Retake says, hello. Hello, Derpel from Retake. Hi, Nadia. Hi, Koi. Thank you for joining today. That cat says he owns that house. Yes. Jim D. Park says, yes, this kitty cat plus his siblings do own the house. How old is your cat? He is of a baby age. Jim D. Park, that. Okay, yes. Yes, indeed. Was that your question, Nadia? How old is your cat? If you drop your car, will it land on its feet? If so, try it. If I drop my car, well, my car, I'll try to drop it, but it's kind of heavy for me to lift it up. But this kitty cat, well, he is resting at the moment, so probably not. Jessica, let me read all your names. Mel D says no. No to what, Mel D? But I like your name. Jessica says hi. Hi, Jessica. Nadia says yes. Melody says no. Ian Taylor says hi. Hi, Ian. Melody says no, I-O. Good. Derpel from Retake says your cat is cute. Cat I mean says Koi. Floofy Kitty says cat. Yay. Yes, indeed, this is a cat. Melody says no. Lots of Dovebirds says to fly high. What kind of cat is it and what is his name? His name, Soul Knight. Yay, Soul Knight says what kind of cat is it? This is a domestic short hair kitty cat with maybe a little bit of ragdoll mix because he's so very genteel. And his name is Baji, B-A-J-I. Jessica Southard says hi. Hi, Jessica. Hello B says stuff I can't read at the moment, but I will be happy to use the translator. Mel D says he is so cute. Thank you. Shout Me Out says to shout me out. I think Nadia says, what's the cat's name? Baji. Hello, ONDRB. You spell my name wrong. It's OINDREEBEE. You are a racist bro. Okay. Nina says an emoji. Hi, Nina. You're not shouting me out because I'm Arab. Oh, I'm a proud Iraqi. Welcome to Iraq. I dare you to throw your phone. No, thank you, Koi. I just have the one phone. Nadia says, I am Arabic too. Great. Awesome. Welcome to Nadia. Welcome to all of the Arabic people. Allah says something. Sorry, I can't read it. I wish I could read Arabic, Allah. Gaming Girl says, I love your cat. Thank you so much, Gaming Girl. I hate... Oh. We won't say hate comments. I think you're trolling me, but that's okay. Thank you for being here nonetheless. And thank you for joining the live. Thank you so much. Really wish everybody well today. Good evening, good evening, good evening. We go live pretty often. We show the kitty cats. See, there's one more kitty cat right there. And we also talk about interesting topics, but I love to catch up with all of you first. So thank you so much for all your highs and hellos and messages to get yourself introduced. I love your cat. It's cute. Koi says, I dare you to shut up. Okay, Koi. I see your message. Keep on sending messages. I will shout it out. Gives you a little bit of visibility on this planet here. Nadia says, yeah, it's kind of mean. Just if you don't have something nice to say, then don't. Please shout me out. I'm so nice. Got it. Yeah, no, it's all good actually, because it gives me something to get the live started with all these different comments of you guys. Thank you so much for being here. Welcome to the live. Get yourself settled. I'm so nice. I love you. Thank you. Thank you. Your profile picture is nice. No, pretty much sometimes I have a moderator and they're very strict. I'm myself not so strict. Pretty much you can say almost anything. Probably won't bother me too much. No, do not do this. Okay. Koi says, I'm sorry. I love you. Love you too. Thank you for being here. Thank you, thank you, thank you. Love having everybody here. Welcome to the channel. Welcome to this live. Nadia says, I sub. Thank you, Nadia. Love it. I love your name, Nadia, by the way. It's very pretty. Thank you for being here. Okay. I am subbed. Good. Great. Awesome. Thank you so much, everybody. Happy Saturday to you. Is it Saturday? Hey, Google. What day is it today?
Today is Saturday, December 7th.
Wow. Saturday, December 7th. So we are in Boston. We have, kitty cats for you to look at. We have kitty cats for you to hang out with. Sometimes these lives are very soothing, relaxing, peaceful content. I think most times it is the case. Sometimes we even play with the kitty cats with the laser pointer, and that has been fun lately. Nadia says, thank you so much. Yeah, of course. Of course. Yeah, Nadia, thank you. We have also been covering physics actually on these lives. Nadia says, do you all know the song Apote? Yes. Yes, APT, Apote. Yes, indeed, I think I have a short using that song. I know it was a hit song, so... It's my friend's birthday. Can you say happy birthday, Hassan? My Sharmuta. I want to surprise him or something from America. Yes, of course. Happy birthday to your friend, Sharmuta. Happy birthday. Best wishes to you. May you have a very wonderful year ahead. It's my favorite. Oh, wow, Nadia. The Apati song is your favorite. Okay. That's cool. I'm trying to remember how it goes. I'm thinking of a different song. but I've used it. I've used it for sure. I've used it. Thank you. Yes, of course. Thank you, and happy birthday to your friend and anybody else's birthday too. Actually, my friend, a childhood friend of mine, his birthday was yesterday. He's in India. It's my childhood friend from India. Actually, a lot of people that I know have their birthdays this month. So everybody who has a birthday in December, happy birthday to you. Amazing month for a birthday. It's a little cold here in Boston, but overall a great month to have a birthday in. So I do think that some months, I seem to have more people I know that have birthdays during that month. And December is definitely one of them. So happy birthday to you. Happy birthday to you. Okay, so shall we talk a little bit about cosmology? This is something we talked about last night, and I was kind of half there, half not there. Sorry about that if you were there. Actually, many of you were not there. It was a very lonely live, and I think I was just kind of feeling tired and sleepy, but I covered some of the content that I wanted to cover. It was a little not the most polished, smooth thing to do, but it's fine. It's don't you want me like I want you, babe. Don't you need me like I need you. No sleep tomorrow, but tonight go crazy. All you gotta do is just meet me at the a party. That's how you sing it. Yeah, no, thank you so much for sharing the words. I just can't remember the tune. Don't you want me like I want you, babe? Don't you need? I can't remember the tune. That's the issue. You know what I mean? Like I've got a different song stuck in my head. Actually, maybe I can sing a song for you guys. Is there a so I know a lot of Bollywood songs. Is there a song I can sing for you? Uh Maybe I can do that to make up for the fact that I can't remember your favorite song, APT or Aparte. Apartmente, maybe, I don't know. So maybe there's a different song I can sing. Let me know, Nadia and others. So you're welcome. Good. Yes, of course. So, I feel like yesterday's live, the Physics Friday live, I should have gone live a little bit earlier. It's okay, it's in the past, but I'll try to go live sort of a bit earlier than we did last night because I think many of you might have gone to bed and many of you were not really there, which is okay. I think if you can catch it later on as a video upload, that works too. You're welcome. It's okay. You can remember it next time. Okay. Yeah, of course. Nadia, do you have a different song? J-Bo says, Kitty. Hi, J-Bo. Hello. Hello, hello. Hello, hello, hello. Kitty, yes. This is a kitty right here. Aparte means apartment. Yes, I figured it is that. I figured it means apartment. I think it's in Japanese. Oh wow. Oh, goodness, yeah. That's awesome. I was going to say that might have been what it was, but I didn't look it up enough to know. Kitty is either shy or tired. Yeah, he's tired. I mean, they just had their food. Pretty much, he likes to nap in between all the meals, and he will wake up if I, play the laser pointer with him. It's his favorite toy, but at this time, I'm letting him rest. Trig But D. Oh no, I don't think you mean that. And welcome to the live. Rude, yeah. Sometimes people are rude. I think they just want attention, and that's okay. Everybody deserves love and attention. So I understand if you didn't get it somewhere else, you might want to get it here. I love her cat. Just kidding. Good. See, Trig has come, has become more nice now. I was just kidding. I love him. Oh, thank you. Nadia says, I love her cat. Thank you, Nadia. Trig Butte D says, I was just kidding. I love him. Well, thank you so much, Trig. I love your name, Trig, trigonometry. Trig is sometimes difficult for people, but in this case, you are named Trig. You must be really good at Trig. So basically, you guys keep on sending your comments and chatting in the live chat. Love to see it and love to read your comments and love to read your names as well. Love to do the shout outs. I will tell you what we talked about last night in case you missed it. So we talked about this book, Modern Cosmology by Scott Dodelson, and we got into the first chapter of it, and this is called The Standard Model and Beyond. Now, we didn't really cover too much of the beyond in this particular chapter. I think it was just kind of getting, started. 6 people watching is crazy. Nadia says okay. Nadia says lol. 6 people watching is crazy. What do you mean? Is that too low? Too high? So we talked about existence of dark matter and perhaps even dark energy, the need to understand the evolution of perturbations around the zeroth order, smooth universe, inflation, the generator of these perturbations. So basically, Nadia says 8. What does Kitty think? Okay, good. Too high, not 6. I only get 1. Oh, haha. J-Bo says, what does the kitty think of cosmology? He loves it. So he loves cosmology. So, in this chapter, we talked about how we have some very good evidence that the universe is expanding. So this means that early in its history, the distance between us and distant galaxies was smaller than it is today. It is convenient to describe this effect by introducing the scale factor A. So we talked about a scale factor A, these little boxes that were getting bigger and bigger. And then at earlier times, A was smaller than it is today, is what we said. And we can picture space as a grid, which expands uniformly as time evolves. Points on the grid maintain their coordinates. So the co-moving distance between 2 points, which just measures the distance between coordinates, remains constant. So we talked about this type of stuff yesterday. I'm summarizing really quickly for you so that you kind of get up to date with it. Oh, haha, I only get one subscriber. Sometimes I only get one, and that's okay. Even one person chatting about cosmology is better than none. In fact, sometimes I chat with myself about cosmology, and that's fine too. No worries. 14 people is great, guys. Make sure you follow it. Thank you, Nadia. Yes, please. Thank you so much. Noa Kawe Ka Gaming says Noa. Hello, Noa. Jabo says, Kitty not paying attention. He is learning in his sleep. Sit on your cat. No, of course I'm not going to do that. Thank you. So we talked about this co-moving distance and a way to basically quantify the fact that the universe is expanding and the distances between us and distant galaxies is increasing. And we will talk about how this was kind of confirmed as well later on in the chapter, but we got introduced to this concept. And we also learned, in addition to the scale factor and its evolution, so one big thing that comes out of this particular chapter is that how the universe behaved or evolved and what its content mainly has changed over time. So you will see how they will make a relationship with this scale factor A, and this type of relationship will come up again and again. So sometimes it's A to the, some number, sometimes it's A to the different number. So this type of content change is also going to be happening. Why would she do that, Koi? Thank you, Nadia. Nadia is an excellent moderator of this chat. She has been most helpful. Thank you, Nadia. So we will get into this, but I wanted to give you a summary of why this A scale factor. So I introduced the scale factor A last night, but I'm just going to make it known again today here. When I say small a or A, that's what I mean. It's going to be the scale factor that we have defined here in this book, where the physical distance is proportional to the scale factor, and the physical distance does evolve with time, as in the physical distance will get bigger and bigger between things over time. You're welcome. I do like it. Oh, I do it and my cat likes it. You're welcome. Can I collaborate with you? J-Bo says don't say. Yeah, that's good. There are 3. So in addition to the scale factor and its evolution, the smooth universe is characterized by one other parameter, its geometry. There are 3 possibilities: flat, open, or closed universes. So we spent some time talking about this as well, actually. Depending on how you come up with the model of the universe, you might get 3 different types of universes. So you could do the math for a model of the universe which makes it flat. You could also do the math for a model that makes it open, or you could even do a model that makes it closed. And there are certain things in the equations that when you finagle them, you get, a different scenario for the universe. And then, of course, after you've done the math, you can compare it to some observations to see which is best fitting your math. And accordingly, you can say the universe is flat or open or closed. At this time, we believe with a great confidence that the universe is actually flat. So we will read a little bit about that here as well. You're really helpful. Oh, thank you. And I love, love, love your voice. Oh, thank you, Nadia. Thank you. The kitty cats actually love my voice too. That's kind of how this channel got started. So the channel was, all kinds of things because I like making content, but then mainly because I make a billion videos and pictures of my kitty cats, I started doing that, but I realized that they actually sleep very peacefully when I'm talking. So they also like my voice. So thank you. Thank you so much for confirming that the voice is working. Kitty thinks the universe is mouse-shaped. Yes! Oh my gosh, Jabo. You're right. It really depends on your own view of things. So that's a great point you have there. Do you know that Chinese people eat cats? I don't think they all eat cats. But yeah, no, I don't know actually. I haven't never seen one eat a cat, so I don't know. Anyways, these different possibilities, so the flat versus the open versus the closedness of the universe, which shape is it, right? These different possibilities are best understood by considering two freely traveling particles which start their journeys moving parallel to each other. A flat universe is Euclidean. The particles will remain parallel as long as they travel freely. General relativity connects geometry to energy. So this is something we talked about in some previous live streams. Lots of previous live streams we talked about Einstein's general relativity and how it connects geometry to energy. And it says that gravitation is basically a curvature of space-time. Accordingly, a flat universe is one in which the energy density is equal to a critical value, and we will approximately see approximately it is around 10 to the minus 29 grams per cubic centimeter. So basically, we actually saw this a little bit in the book, Einstein's Cosmos, by Michio Kaku, which is based on Einstein's life and his contributions mainly to physics, as well as some other things that were going on during his time, such as the developments in quantum mechanics, the wars, things like that. And we had seen that basically when he came up with the equations for general relativity, depending on how you treated your density in the universe, you either got a flat universe or an open universe or a closed universe. So it's almost like the mathematics is possible for all three types of situations or geometries, if you will. Right now, we think it's mostly a flat universe. Gotta go, but thank you. Yeah, thank you for being here. Can I get a 360? 360. Well, let's give you a 60. Just a 60 for the moment. If the density is higher than this value, so the value we just said, 10 to the minus 29, right? If the density is higher than this value, then the universe is closed. And so so in this case, if the universe is closed, then gradually the initially parallel particles will converge. So it's almost like they will, in the flat one, they don't meet. They're parallel if they're moving freely. In the closed one, they will eventually converge. Kind of like how our lines of constant longitude meet at the north and south poles. So like closed example would be like our Earth. It has a curvature that is spherical, so all the lines of the longitudes meet in the poles. So then the analogy of a closed universe to the surface of a sphere runs even deeper. Both are said to have a positive curvature, the former in 3 spatial dimensions and the latter in 2. Finally, a low-density universe is open, so that the initially parallel paths will diverge, and they would basically never meet. They would just get farther and farther away from each other. So, to understand the history of the universe, we must determine the evolution of the scale factor A with the cosmic time t. So this is small a and small time t. So basically, after introducing the scale factor of small a, we can start to understand how it affects our math and how it kind of appears in these equations. So I won't get into too much detail of the equations because I know that can be hard in a podcast style of content here, but I'll give you some overall description, hoping that that kind of helps with your understanding of the universe's evolution here. And we're still in very early days anyways. We're not like in the depths of this business yet, so think of this as an introduction really to the cosmological studies that we will get into. Jabo says bye. Bye. You're just going to assume I eat cats because I'm Chinese. Oh no. Koi, that's not true. I did not say that, and I'm sorry. Okay, great. Nadia and you are talking. Good. To understand the history of the universe, we must determine the evolution of the scale factor A with cosmic time T. So basically, how the scale factor changes with cosmic time is something we will take a look at. Again, general relativity provides the connection between this evolution and the energy in the universe, and how the scale factor increases as the universe ages, and the dependence of this small a on small t varies as the universe evolves. So how this is what I was mentioning earlier. At early times, so after the universe came to be, at early times, A is proportional to T to the 1/2. So that's the sort of relationship that A has with T. While at later times, the dependence switches to A going as T to the 2/3. So that's very different, right? So this is another way of saying that the universe, how it behaves, is going to be different based on its age. So when the universe was quite new, the scale factor A was going as T to the 1/2, but later on it switches to T to the 2/3. So the universe now, for example, is very different than when it was a young universe. And of course, that should make sense because, now we have you, me, human beings, cats, trees, planets, moons, suns, stars, stars and things like that is a much more mature it's basically we're now a much more mature universe. In the beginning, in the very beginning, there were no people, there were no cats, there were no trees, there were no stars even. So in those early days, how things were, what the dynamics were, and what the content of the universe was, is very different to what it is now. But we would like to understand how things have evolved and how things have changed so that we can understand maybe what happened then, and also so that we can answer some very important open questions at this time, which is actually related to dark energy and dark matter. We will get into those topics later on, but we still have some, let's just say, even today, even after learning a lot of things, we still don't know some very important things. So by understanding the evolution of the universe, we hope to answer some of the questions that are pending today, even today's date. So how the scale factor varies with time is determined by the energy density in the universe. So this energy density situation is going to be very important as well. So we just said that the scale factor used to go as T to the 1/2 in the early days. It goes as T to the 2/3 now. So what changed? Actually, the universe's content has changed a lot. It has gone through a lot of changes and evolution. And basically, this energy density concept that we're going to be talking about now is what kind of affects that. At early times, one form of energy, radiation, dominates. So what is radiation? Radiation is basically light. It's basically photons. So when the universe was like really new, baby universe had more photons. And so its energy density was the content of the content of the universe really was more photons, was more radiation, according to this book, at least, and I think according to many cosmologists. We're using a textbook right now, so hopefully it's pretty established that we understand this. But I should mention that, according to the cosmologists, at early times, this one form of energy, which is really radiation, that dominated, while at later times, non-relativistic matter accounts for most of the energy density. So because energy density was mostly radiation in the beginning, scale factor was going as T to the 1/2. Later on, when energy density is more to do with non-relativistic matter or becomes more matter dominated, then A or the scale factor goes as t to the 2/3. These types of relationships will end up being very important in our overall understanding. So bear with us. But that's what's kind of going on. Nadia says, I love you, but I need to go. I will come back in 5 minutes. Okay. That's okay, Nadia. We'll see you back here in 5 minutes. Bye. Love you. Yes, love you too. In fact, one way to explore the energy content of the universe. So basically, some of this is theory and what people predict, and some of this is observation and a way to confirm what we have seen, right? So basically, if we say that if we measure, say that there is an established way to measure the scale factor's dependence on time. Say that we know to a very big confidence that it was going as t to the 1/2 in the beginning, or sorry, not in the beginning, but in the early days. I'm not sure that we know exactly what it was in the very, very beginning, but say in the early days it was going as t to the 1/2. Now it goes as t to the 2/3. So we know, well, that has to do with the energy density changing. In the early days, it was mostly radiation. Later on, it was mostly matter. So that's what has given this difference. So then, if we want to say, if we want to then ask the question from the other direction, how to explore the energy content of the universe, well, you could actually measure changes in the scale factor, because that would basically give you the energy density of the universe at different times. So is there other periods of time during which this scale factor may have changed? Is it changing now? Has it changed recently? And those things will all kind of give us the energy density or the content of the universe. And you will see later on that this actually is very important for both dark energy and dark matter. And hopefully can even help us to determine these things after we've made even more measurements of the universe. We will see that partly as a result of such exploration, so the exploration where we try to measure changes in the scale factor, we now believe that very recently the scale factor, has stopped growing as t to the 2/3, a signal that a new form of energy has come to dominate the cosmological landscape. So you will see that this is going to be very important. It's no longer the matter-dominant type of universe anymore. And you will see that this will actually give us dark energy. So very interesting indeed. We will skip over the next part because we kind of covered it yesterday. I just wanted to give you an overview of the beginning of this chapter, how things were kind of getting started here. And then we will move on. So we will, let me see. We will go to this part. I'm trying to see where is the next bit that can be helpful for our understanding and a summary. So basically, we will get to this part. I think I kind of covered how measuring the scale factor can tell us about the energy density of the universe. So by the way, if you're interested in knowing how they do that, there's more information there that we actually covered yesterday. It's they measure redshifts, and they try to get different points of reference basically to make this measurement. In page 9 of this chapter, there's more information about this, something like Cepheid variables or stars for which intrinsic brightness is tightly related to period. Hubble Space Telescope measured the periods of thousands of Cepheid variables in galaxies as far away as 20 megaparsecs. So there's a lot of different measurements that go into this type of work. Next, we will summarize for you the Big Bang nucleosynthesis. So I've given you some idea about scale factor, small a, and cosmic time, small t, and how scale factor depends on time. Scale factor was going as t to the 1/2 in the early days, and it was going as t to the 2/3 later on. And this change happened because the content of the universe changed. The universe in early days was mostly radiation or photons, and later on it became more matter. So as the content of the universe changes, the scale factor's behavior also changes. And actually, this is going to be incredibly important in our understanding of dark energy and dark matter. And so more measurements are going to be needed for this because basically we noticed that the scale factor has changed again. It's no longer going as 2/3. And now the way it is actually giving rise to this new form of energy that we need, which is dark energy. But we will also learn a little bit about dark matter in this particular part that we're on right now, which is Big Bang nucleosynthesis. So the nice thing is that the universe in its early days was more simple. And when the universe is just getting started from the Big Bang, which we have also confirmed now, basically because there wasn't much at that time in terms of matter, it's almost like you can kind of picture it in a more simple way. Like right now, we have lots of elements. You and I, we're made of a bunch of elements, but back when the universe was just getting started, the most abundant element, even now, the most abundant element in the universe is just hydrogen. So for something, for elements to actually form, for nuclei to form, the universe had to cool down a lot more. So people can actually make estimates of how much of any given stuff there was, and we can try to make some measurements to see if these agree, and basically learn more about the universe and other things that may or may not be there from this type of environment. So when the universe was much hotter and denser, when the temperature of order and MeV, there were no neutral atoms or even bound nuclei. So this is something that people, once you kind of think about it, it'll be clear to you. But it can be easy to forget that we were not here in the beginning of the universe. The elements were not there. To make elements, to make even a nuclei or a nucleus or a bound nuclei, neutral atoms, to even just have atoms, you need a certain level of stability and cooling, which we did not have in the very beginning of the universe. So there were no, elements, there were no helium, no lithium, no nothing. Maybe very tiny amounts of hydrogen, because even to make hydrogen, you need a stable atom. And if things are so hot, even hydrogen can't really exist yet. So that's where we are now. We're in the very early days of the universe, okay? So we've come a very long way. We can make elements now. They're made in stars, and when the stars die, they spew the stuff everywhere, and that's how we come from stars as well. All the things that we're made of, those elements are made in stars. But the whole making stars, all of this is much later in the universe. This is still not happening yet, where we are in this particular part of the story. So we're in the part of the story, universe much hotter and denser. The vast amounts of radiation in such a hot environment ensured that any atom or nucleus produced would be immediately destroyed by a high energy photon. So at this point, the photons are really the king of the world, Photons are light or radiation, like I was saying earlier. Basically, the scale factor, when it was going as T⁻², radiation was the most important thing in the universe. And just imagine, it's hot, it's dense, it's a bunch of photons. And even if there is something trying to make an atom, it's just going to get blasted with photons. And it won't be able to make up an atom. There won't be any hydrogen. There won't be any helium. There won't be any lithium. There won't be any you and me yet. You and me come much later. Much later. So, and again, even today, the most abundant element in the universe is still hydrogen. Even our sun is still making helium from hydrogen. So just to make helium even is a big deal. Our sun is making that. That's how we get light and power and heat from the sun. It makes helium from hydrogen. That's how it stays alive and does not collapse on itself upon its own gravity. So making heavier and heavier elements is a very big deal. It's a much more complicated thing. It cannot be taken for granted. And certainly it was not happening in the very beginning of the universe. So as the universe cooled well below the binding energies of typical nuclei, light elements began to form. So light elements, this is hydrogen and helium mainly. Maybe little bits of lithium, but in the very, 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 very beginning, even making hydrogen is going to be a big deal, and then maybe little bits of helium. So Number one most abundant element would be hydrogen, followed by helium and very little lithium. All the other higher elements in the periodic table come later on. And some of them require much more complicated processes that can only really happen in the environment, such as a star. So, what's your Cash App? I don't know what my Cash App is, but my PayPal is in the link in my bio if you want to donate. So, knowing the conditions of the early universe and the relevant nuclear cross sections, we can calculate the expected primordial abundances of all the elements. So, this is so very important. Knowing the conditions of the early universe and the relevant nuclear cross sections, we can calculate the expected primordial abundances of all the elements. So, primordial abundance. Primordial meaning universe is very new still. Abundance meaning how much of each element there is, right? And so, by the way, in astronomy and cosmology, anything that is above helium is called a metal. Generally speaking, at this point of the story, we're really talking about the light elements like hydrogen, helium, maybe a little bit of lithium. I don't think we would make much more beyond that at this point. But yeah, those are certain definitions to keep in mind. Okay, a lot of astronomers. This is cosmology, which is separate from astronomy, but has a lot of overlap with astronomy. But astronomers typically say metals when they mean over helium. I know metals in the context of chemistry is something else, but in astronomy, everything above helium is considered a metal, quote unquote. Okay, so basically the theoretical, so they talk about certain things that they predicted. Basically, they predicted a certain amount of baryons. At that point, so what are baryons? Baryons are basically protons and neutrons. The theoretical predictions, which we will explore later on, depend on the density of protons and neutrons at the time of nucleosynthesis. So after the Big Bang, basically, as nucleosynthesis sort of starts to happen, as things sort of start to cool down, you'll get protons and neutrons. And the combined proton plus neutron density is called the baryon density. So in cosmology, they're basically lumping together protons and neutrons and calling them baryons, just for convenience or something. Like it's just a convenience thing. They don't want to deal with more specifics than that. So baryon density, since both protons and neutrons have baryon number 1, and these are the only baryons around at that time. Thus, Big Bang nucleosynthesis gives us a way of measuring the baryon density in the universe. So basically, if you go through the process of Big Bang nucleosynthesis, like you have the math of that from all these different cross sections and things that you would expect, as things cool down. Basically, you would get some way of measuring the baryon density in the universe. Since we know how those densities scale as the universe evolves, they fall as a to the minus 3, we can turn the measurements of light element abundances into measures of the baryon density today. In particular, the measurement of primordial deuterium pins down the baryon density extremely accurately to only a few % of the critical density. So this is very important. Once we know the baryon density and have a way of measuring it, then kind of understanding what things were there then becomes more clear, and also what things we don't understand become clear. So you'll see this in just a second. Ordinary matter, that's baryons, protons and neutrons, contributes at most 5% of the critical density. Since the total matter density today is almost certainly larger than this, direct estimates give values of order 20 to 30%. Nucleosynthesis provides a compelling argument for non-baryonic dark matter. So this is another way in which we actually get evidence of dark matter, is from this nucleosynthesis. So that's pretty crazy. That's I think really interesting. We basically traced back all those days ago, all that time ago, the baryon density we got, and the measurement of primordial deuterium pins down the baryon density extremely accurately to only a few % of the critical density. ordinary matter contributes at most 5% of the critical density. So there is a critical density, and ordinary matter is accounting for only 5% of it. This is really crazy. Since the total matter density today is almost certainly larger than this, direct estimates give values of order 20 to 30%. Nucleosynthesis, so the number that is 20 to 30%, ordinary matter is contributing only 5% to that number, which is why we think that the rest of it is dark matter. So dark matter is around 23%. So this whole discussion about the energy density, what they measured it as, what they think the baryonic density is, which is the ordinary matter density, and what the number should be versus it is found to be. This is yet another way of getting dark matter. The deuterium measurements are the new developments in the field. These measurements are so exciting because they explore the deuterium abundance at redshifts of order 3 to 4, well before much processing could have altered the primordial abundances. So they're looking really back, and at that time, there wasn't much more processing happening to be able to make other things really, like heavier elements, which would have changed the primordial abundances of these things that we're collecting. The basic idea is that light from distant quasars is absorbed by intervening neutral hydrogen systems. The key absorption feature arises from the transition of n equals 1 ground state of hydrogen to the first excited state, requiring a photon with a wavelength of around 1200 angstroms. And since photons are absorbed when exciting hydrogen in this fashion, there is a trough at that same wavelength, redshifted by a factor of 1 plus z. So this is how they basically measure how much deuterium there was, and they can make a very, basically they can very confidently measure. It's pretty cool. It's really cool, actually, what they do here. But at the same time, it's kind of nice because at that time, if it's mainly just hydrogen and hydrogen's cousins, then, you know, we have a way to measure that. It's not the most hardest thing in the world. Maybe it is, I don't know. So basically, this is how they translated in the, note that the steep decline in deuterium as a function of baryon density. So there is this picture here, helps here. Even relatively large errors in deuterium measurements translate into small errors on the baryon density. So they think that they have not made too many, errors in this baryon density measurement. And basically this difference that we find in the needed matter density versus what we actually find the ordinary matter to be contributing to, there is still that big difference. So we said that right now the verdict is dark matter is around 23% of the universe, which is high. And because, we say that 73% or so is dark energy, then 23% or so is dark matter, and the rest is ordinary matter. And so everything we understand is a very small portion of the of the total, what there is to understand in the universe, and what there is in the energy content of the universe. So that's this sort of stuff is part of the calculation when people say those things about why they're confused about dark energy, dark matter. Not confused, how they quantify how much there is in dark energy and how much there is in dark matter. So next, we also talked about the cosmic microwave background. This is an immensely important measurement that we've made of photons that are from around when the universe was around 300,000 years old only. So the universe is very old at this point, billions of years old. We think it's around 14 billion years old. So imagine when the universe was only 300,000 years old. That's really pretty new for the universe. And we have collected some photons, and we call that the cosmic microwave background radiation. And these photons, the last scatter that they did was off of electrons at a redshift of around 1100. And since then, they have traveled freely through space. So when we observe them today, they literally come from the earliest moments of time. So us observing photons that are this old is really a very special thing. So when the cosmic microwave background was first measured, and then lots and lots of other experiments also measured it, and we have, they got the same thing. basically because they have a picture of the universe at that point in the early days, right? And the same picture was obtained again and again. So it's very confidently known at this point. I kind of had, wait a minute, I'm going to try to find it. I have the CMB here somewhere. I don't want to waste time. I will show you the picture at some point here soon. So when we observe these photons today, they literally come from the earliest moments of time. They are therefore the most powerful probes of the early universe. So you'll see how the CMB photons are really, really important. Cosmic microwave background photons are very important. We will spend an inordinate amount of time in this book working through the details of what happened before the epoch of last scattering and also developing the mathematics of a free streaming process since then. A crucial fact about this history, though, is that the collisions with electrons before last scattering ensured that the photons were in equilibrium. That is, they should have a black body spectrum. So they were expecting these photons to have a black body spectrum. And, oh, hi. Hi, Nadia. And be able to basically pick up on a black body radiation. Because the universe, just like anything else, is a black body. So if at some point there were some photons after they have done some business scattered off of some electrons, and we look back in time, we should be, because if we look back very far into time and distance, we should be able to pick up on a black body radiation, basically, of the universe itself. And we did. And it's the same thing as the CMB photons. So, and there is a very famous picture of it that I also have sort of as a magnet somewhere that I can try to find. Basically, and they found remarkable agreement as well between different observations of this. So we have been told that detection of the 3K, this is 3 Kelvin background by Penzias and Wilson in the mid-1960s was sufficient evidence to decide the controversy in favor of the Big Bang over the steady-state universe. So this also told us about the Big Bang way of originating the universe. Penzias and Wilson, though, measured the radiation at just one wavelength. If even their one wavelength result was enough to tip the scales, the current data depicted should send skeptics from the pages of physics journals to whatever, blah, blah, blah. So basically, they're saying that there's no doubt about this. The most important fact that we learned from our first 25 years of surveying the CMB was that so this is old news now. It's been like 25 years since the CMB was first discovered. And so we have a picture of the CMB quite literally, it's sort of this like ellipse looking thing. And there's this there's a picture. I'll show it to you at some point. I'm kind of surprised that there is not a picture here. Like, it's a color photo, so the most well-known picture of it is a color photo of it. So anyway, I will find it and show you, but basically this is old news. For 25 years they've been surveying it, at this point even longer. And what that has told us also is that the early universe was very smooth. No anisotropies were detected in the CMB. This period, while undoubtedly frustrating for observers searching for anisotropies, solidified the view of a smooth Big Bang. We are now moving on. We have discovered anisotropies in the CMB. So in the first 25 years, they didn't really think that there was any anisotropies or any lack of a homogeneity in the CMB. But now, upon looking more and more, they actually have found little perturbations. And these tiny, whiny, small perturbations in the cosmic plasma are something to understand, and the author thinks that they might actually hold secrets to dark matter. So these perturbations of the smooth universe. So you'll hear about this. Smooth universe, what they mean is the cosmic microwave background picture. It was very smooth. It was very same looking everywhere in the whole picture. And finding little perturbations in it is kind of difficult. And also the first few times it was observed or collected, since they've spent so long on it, there are people who do CMB stuff like their whole career, basically. So Now there might be a little bit more coming out now, and they're finding these perturbations, and those perturbations will be very important to understand. Pretty much understanding the CMB is so very important because it's from such an early time of the universe. It can easily hold a lot of secrets, of course. So, while the three pillars put the Big Bang model on firm footing, other observations cry out for more details. I hinted above at one of these, the notion that there must be non baryonic matter in the universe. Dark matter is a familiar concept to astronomers. Of course, we've seen some dark matter candidates in other live streams here. But basically, because of the limits inferred from Big Bang nucleosynthesis, the dark matter, or at least an appreciable fraction of it, must be non baryonic. So the cosmological or the cosmologist viewpoint is that cosmologists have some estimates of baryonic versus non baryonic matter. And they think that dark matter, because of all this math we just discussed, is non baryonic. It is not made of ordinary matter. What is this new form of matter? How did it form in the early universe? The most popular idea currently is that dark matter consists of elementary particles produced in the earliest moments of the Big Bang. Wow. So, yeah, because of this view, you can understand how important it is to understand the early universe. Because maybe dark matter and its origin is so deep in the early universe's history that we can't easily probe it. But if we probe the early universe more and more, maybe we can find some clues. So, yeah, in chapter 3, we will explore this possibility in detail, arguing that dark matter was likely produced when the temperature of the universe was order of hundreds of GeV. As we will see, the hypothesis that dark matter consists of fundamental relics from the early universe may soon be tested experimentally. So hopefully, there are lots of plans and experiments to try and do all these things that we just don't have the results from yet. The last decades of the 20th century saw a number of large surveys of galaxies designed to measure structure in the universe. These culminated in two large surveys, the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey, which between them will compile the redshifts of and hence the distances to 1,000,000 galaxies. So, we will have 1,000,000 galaxies worth of data as far as the distances and things like that. So it should really give us a tremendous amount of data going forward. Galaxies are clearly not distributed randomly. The universe has structure on large scales. So this is another whole topic. The universe, as it has evolved from its early days, we see that galaxies are not just randomly distributed in the universe. The universe has some sort of structure at large scales, and people would also like to understand how that forms. How does structure form at all in the universe? And maybe there will be clues of dark energy and dark matter in the structure formation. So some people literally study structure formation. You will see people say, "Oh, what are you talking about? What are you doing? Structure formation." What do they mean? They mean universe's structure. To understand this structure, we must go beyond the standard model, not only by including dark matter, but also by allowing for deviations from smoothness. So, basically, at first, when I saw this chapter and he said beyond the standard model, I was thinking something else, but I think he's basically saying that dark matter is not part of the standard model of particle physics. Particle physics standard model has given us the more known families of particles that we know and love: leptons, quarks, bosons. But he's saying that dark matter is something else because it has to be non-baryonic because of the thing we just discussed. So I think that's what he means. Like, it's not beyond standard model. Some people in particle physics would think of that as something else, but anyway, he's talking about dark matter. Okay, got it. We must develop the tools to study perturbations around the smooth background of the standard model. And so basically what he's suggesting, this particular author, is that it's really by studying the perturbations around the smooth background. First of all, he thinks that that's going to be very important. And, second of all, the structure formation might have secrets revealing more things about dark energy and dark matter. That's what he's saying. So the best ways to learn about the evolution of structure and to compare theory with observations are to look at the anisotropies in the CMB and at how matter is distributed on large scales. So those galaxies having some, distribution Again, that's what he's saying. To compare theory with observations, we must at first try to avoid scales dominated by non-linearities. As an extreme example, we can never hope to understand cosmology by carefully examining rock formations on Earth. The intermediate steps, collapse of matter into a galaxy, molecular cooling, star formation, planetary formation, etc., are much too complicated to allow comparison between linear theory and observations. So something I mentioned last night too is that astronomy is much more specific. Astronomy looks at objects in the night sky, like a star and a star's evolution or its death. That's astronomy. That's like a very much more specific and sort of small scale thing when you compare it to cosmology, which is more about the entire universe. So when you try to understand things about the universe, you might have to kind of step away from the usual thinking, which is far more specific. Like, it's not about this galaxy, it's not about this solar system, about this Earth, about the neighboring galaxy, even. It's about the entire universe, right? So, really, really step back and understanding how the universe's structure formed and how matter seems to have distributed itself in the universe. That is, first of all, it requires a lot of measurements that support that, but also it's a very different way of thinking than generally people might think in terms of astronomy, astrophysics, and things like that, which is why this is a separate subfield, which is cosmology. So, yeah, while perturbations to the matter on small scales have grown nonlinear, large-scale perturbations are still small. So they have been processed much less than the corresponding small-scale structure. Similarly, anisotropies in the CMB have remained small because the photons that make up the CMB do not clump. Ooh. Identifying large-scale structure and the CMB as the two most promising areas of study solves just one issue. Another very important challenge is to understand how to characterize these distributions so that theory can be compared to experiment. Oh, thank God. It is one thing to take to look at a map and quite another to quantitative tests of cosmological models. Yeah. To make such some map as in the CMB kind of looks like a map. To, a very colorful, pretty map, but a map sort of. To make such tests, it is often useful to take the Fourier transform of the distribution in question. As we will see, working in Fourier space makes it easier to separate large from small scales. The most important statistic in the cases of both the CMB and large scale structure is the two-point function called the power spectrum in Fourier space. So then he does some more math, and let's see if this will be helpful or not. Ooh, we will just conclude with what he says in the end of this particular part. For now, though the message is clear, dark matter is needed not only to explain rotation curves of galaxies, but to explain structure in the universe at large. So basically, after looking at structure, people think that you need dark matter to understand structure in the universe. And we will actually also see how the dwarf galaxies, people think that certain galaxies, when they're studied, also give you this need for dark matter. So dark matter plays a bigger role than you might think, not only in the fact that we found it, or we found this invisible matter, evidence of it, and that confused us a lot, but also it seems to be very important in large scale structure formation and even in certain neighboring galaxies like dwarf galaxies and things like that. So it's going to be incredibly motivated in many ways when somebody decides to study what dark matter is. Okay. And then, of course, we will also talk about cold dark matter. The theory encompassing all these beyond and standard model ingredients, dark matter plus evolution of structure plus inflation, is called cold dark matter, or CDM. The cold part of this moniker comes from requiring the dark matter particles to be able to clump efficiently in the early universe. If they're hot instead, that is, have a large pressure, structure will not form at the appropriate levels. So there is basically an argument. The cosmological sort of argument about dark matter is that there is something called cold dark matter, or CDM, and there's reasoning behind why it has to be cold. We'll get into it, but basically, long story short, they understand the cosmological point of view is that you need dark matter to form structure. So, if your dark matter candidate is not letting us form structure because it's too hot or too something, then it's not going to work out because we know that there is structure in the universe. So, it has to be consistent with that. So, that's where the cold dark matter concept comes from. And we will get into it a lot more going forward. We didn't really touch upon it in the astronomy point of view because it's not really an astronomy point of view. Cold dark matter CDM is a cosmological point of view on dark matter. So we will get into it in this context. Okay. So yeah, that's what we have been talking about. It took me all this time to just recap what we kind of talked about in the start of this discussion. We're getting into cosmology now. We have talked about physics, astronomy, astrophysics, especially in the 20th century, relativity, and quantum mechanics. But now, as we got Einstein's equations, actually, what has gotten much more mature and full of mysteries is cosmology. So that's why I decided to introduce cosmology to you guys as well on the channel. For the last couple days here now, yesterday and today, we are now into cosmology. Hope you've been enjoying the discussion. I'll hang out for a few more minutes because I actually have to go. I have an appointment tonight for dinner, so I won't be able to make the live super duper long. But I am around for a few more minutes here to take any questions or to say hi or catch up. But this is the type of stuff that we will be continuing for at least some time going forward. And I will actually, what I'll do is next time I will summarize everything again in a more short way. There is a summary of this chapter that I didn't really get to today, but I will start with that next time. No, this is no. Well, let me check. This is no, this is this Robertson-Walker scale factor 4 billion years ago started dark matter dominated era, Hubble time. No, this is basically talking about how you need dark matter inferred even from Big Bang nucleosynthesis. So we have not talked about the Robert Walker type of stuff yet, actually. We will get into it. There might be something more to do with that as we go forward. But Robert Walker has not actually come up yet. This is sort of more deriving it from Big Bang nucleosynthesis and the CMB, and also looking at structure formation, meaning how the universe has structure. The galaxies are not just randomly located. There is a sort of a rhyme to the they're clearly not distributed randomly. The universe has structure on large scales. That's what that is. But yeah, no, thank you for the question. We will definitely get into more of that. Thank you, reading. See you next time. Happy weekend to Baji. Yes, thank you, Heike. We will talk about more details. I think we were just kind of introducing these topics at this point. We haven't gotten into much of the details. The cold dark matter, what you're asking about might come up later on. But yeah, I will start, I think, with the summary of this next time. Let me do this. Let me show you the... Oh, sorry, you're here. I forgot that Suji is sitting in this chair. I was like pulling up the chair. Oh, Shuji. Hi, Shuji. Hi, Shuji. So let me leave you with this. Then you will understand something about what I've been saying. You can look at that. Yes, you can look at that. Great. Okay, I have to drink some water. Some water. Oh man, it's cold. Jackie. I wish you were there last night. We could have had a long discussion. I'll be back again tomorrow, of course. But yeah. Thank you so much, everybody, for joining. Sorry I have to run quickly tonight, but I'll be back again tomorrow, and we will have many such discussions, and I really appreciate any inputs from you as well. So thank you so much. Thank you, and be back soon, and I'll just leave you with this for the minute here. Actually, I'm gonna do this. Sorry. I'll move you over here so I can also charge my phone, actually. Hi, Fuji. Hi. Hello. I think these topics are kind of complicated, right? So it helps to go over it again and again. It's definitely helping me to go over it again and again. So hopefully for you guys too, it'll help to kind of cover it again and again and again and again. And also from different perspectives. Like, you know, dark matter we have covered now. 1 second, let me just check. Yes, this is charging. 1 second, guys. I was saying that dark matter, especially, we have covered now in a few different perspectives. We've covered it from the perspective of astronomy, of particle astrophysics, and as well as now cosmology. And I was kind of hinting at this earlier when I said that, you know, dark matter is one of those topics that it really depends from what approach you're coming from. If your approach is astronomy, it might be something like we looked at some dark matter candidates from the astronomy approach, astrophysics approach, as well as particle physics approach. Of course, these are all overlapping, but then we also get a story from the cosmological standpoint. So I think when we get all of these ingredients together, hopefully we will see a better picture of it. So here you go. This is an important diagram right here, and it kind of summarizes what we just talked about. See, summary, and then all this. So I'll let you look at that for just a second here, for as long as you want, actually. Right here, because I have to have drink some water. There. Okay. I also just thought about a question that I'm gonna ask one of my professors, I think. So once I have the deeper insight on that, I'll let you know as well. Baji. Mama's here, baby. Don't worry. Mama's here. Okay. Off and off and off. Off and off. Okay. I'll be right back, guys. Sorry, guys. I